Welcome. In this video, we're going to determine the heat gained by the gas, also the change in internal energy, as well as the work that is done by the gas in the process. So, the question that we've been given is 3 moles of oxygen are kept in a cylinder with a frictionless piston at 300 kelvins and a pressure of 1 atmosphere. If this gas is heated to 400 kelvins, how much heat is gained by the gas? That is part A. Part B, what is the change in internal energy? And part C, how much how much work is done by the gas in the process? So this is the information that we've been given. So here the data that we've been given is, so here we've been told to use the CP to be 2.3 joules per mole per Kelvin, and the heat capacity ratio, which is also called an adiabatic index, to be 1.4. So from here, what we're going to do is so this is the data that we have. The first thing that we need to do when you are given any question on any topic, the first thing that we need to do is you first collect the data. That is what we need to do. So here, the data that has been given is we have the 3 moles here as the number of moles, and then we have the temperature 1, which is this, the temperature 2, which is this, and adiabatic index, which is the heat capacity ratio, which is 1.4, and the pressure 1 atmosphere, the CP 32.3 joules per mole per Kelvin. Now here we're going to begin with the first question here. So let's just write solutions. So what we're going to do is we've been given this to say find how much heat is gained by the gas. So in a scenario where we have this and we also have this an adiabatic index, which is the heat capacity ratio, the work or the heat that is gained, is given by the NCP delta T, where this is the number of moles, this is the heat capacity at constant pressure, and this is the change in temperature. So here, what we need to do is we just need to, so the constant pressure, the number of moles, and the change in temperature. So what we're going to do is we just need to plug in the values now. So the gas was kept at the constant temperature of, or the constant pressure of 1 atm. And the value that is given is this one. So from here, what we're going to do is let's just plug in the values. We plug in the values, the number of moles, we have 3, times the CP, which is 32.3 joules per mole per Kelvin, times the change in temperature. We have the 400 as the T2 minus 300. All these are in kelvins, and what we're going to do is we're going to cancel the common parameters such that this and this will cancel, and also this and this will cancel. And what we're going to have when we multiply these, we are going to find this is 3 times the 2.3 times 100, which is the difference between these temperatures. What we're going to get is 9690 joules. So this is the heat that is gained by the gas. Now from here, let us now proceed to find, so this is the first part, which is part A. Let us go to part number B, which requires us to find the change in internal energy. So let me just erase this part. We need to keep the data so that we can be following very well. So from here, we're going to write, so part B here. So the internal energy, so the change in internal energy is given by NCV delta T, where this is the number of moles, this is the heat capacity at constant volume, and this is the temperature. So here we know that Cp, Cv, the ratio between this and this is what gives us an adiabatic index here. And so when we make V the subject, what we're going to have is, okay, Cv, this index is equal to Cp. So our Cv will be Cp over an adiabatic index. So from here, what we're going to do is we're going to plug in n times Cp over an adiabatic constant or index times the change in temperature. So here, when we plug in the values, what we're going to have is we are going to have 3 moles, 3 moles. So 3 moles times 32.3 joules per mole per Kelvin times the change in temperature, which is in Kelvin, so that the Kelvin here and the Kelvin here will cancel. The more and more here will cancel. And what we're going to have is, when we punch this 3 times the 2.3 times 100, what we're going to get is 6921 joules. And this is the answer for the second part. So let us now proceed to the third and last part. So under this one, what we're going to consider is the first law of thermodynamics. And the first law of thermodynamics is actually stated as follows. The change in internal energy is given by the heat minus, states that the change in internal energy is equal to energy minus work done. So here, since we have this and we have this, what we need to find is this. So we just need to make this the subject of the formula. When this crosses the equal sign, we are going to have the change in internal energy minus heat is equal to work energy, negative. If we divide through by negative 1, we are going to have work done is equal to heat minus internal energy. So from here, we can just plug in the values. So here for heat, we had 9690 joules, and for change in internal energy, we had 6921 joules. So this minus 9690 minus 6921, the answer that we're going to get is 2769 joules.